Welcome everyone to the final lecture on the course on quantum machine learning. Well done on making it so far, and I hope that you've enjoyed all the lectures and talks with us. So today, to conclude everything that we've learned about quantum machine learning, I really just want to leave you with a whole bunch of open questions and hopefully excite you and encourage you to get into the field of quantum machine learning and to study it and to contribute to interesting research and applications. So the title of today's talk is about the capacity and the power of quantum machine learning. Spoiler alert, most of the things I will probably say is this is interesting, but we have no idea. And it's up to people like you, researchers, people who are interested, curious about quantum machine learning, to go and find out exactly what is possible. So let us begin by discussing, what does capacity even mean? In classical machine learning, capacity actually has a lot of different associations. I think that people use the term capacity a lot with lots of other different things. And this typically gets thrown around interchangeably with statistical complexity, expressivity, the power of a model. But really, we can think about capacity quite simply as how many functions can my model actually approximate? And the more the more functions my model can approximate, then it should have a higher capacity. Now, this might make you think intuitively that you would want a model with the ability to express lots and lots of different functions, right? Because you don't know initially what function you're trying to approximate to model your data. And so having a model that has an ability to approximate any function sounds like a good quality. And so there is this question of, is a higher capacity always better? And it turns out that a higher capacity, even though intuitively might seem desirable, is not necessarily always a good thing. And so how do we understand what capacity means? In classical machine learning literature, luckily, there is a lot of research going into this exact question of how do we understand the function expressibility of our model. And typically what is done is we try to understand capacity in the context of generalization. And if you remember from a few talks before, the idea of generalization is trying to understand how your model will perform on unseen data, on new information. This is the ultimate goal for a machine learning model, quantum or classical, to try and figure out how will it actually perform on new data and new information. We want typically that generalization performance to be as good as possible, and the error associated with new data is called generalization error, and we want that to be as low as possible. So we try to understand capacity in this picture of generalization. And generalization really relates to this trade-off called the bias variance trade-off, where if we look at this graph, we have the capacity of our model on the x-axis. And so models that lie on this side of the axis are kind of deemed as simple, whereas as we move more and more towards this side, we get towards the more complicated models. Now, this bias variance trade-off tells us that if we keep our model too simple, then the model has a very high bias, meaning that the model doesn't look at our data enough to truly learn relationships and correlations and structure that actually exists in the data. And on the other side of it, if we make our model too complicated, if we have our model that has the ability to fit too many intricate functions, well, then our model will start to overfit, and the variance that it has on classifying new data and new information will be very high. And a high variance corresponds to our model overfitting. And so there is this trade-off between having a model that's too complicated, that has too high capacity, and a model that's too simple, too low capacity. And this trade-off is really what affects the behavior of generalization performance and generalization error. So typically we want our generalization error for a model to be as low as possible. And so there is this notion of having a model with the optimal capacity, the optimal amount or expressibility or power, that it doesn't overfit and it doesn't underfit. So it doesn't have a high bias and it doesn't have a high variance. Now, choosing a model with this optimal capacity, of course, is not easy. And in fact, thinking about what capacity even means is arguably still an open question. How do we even measure the capacity of a model? So let's look at what is actually explored and done in classical machine learning literature. This is always a good place to start. What is done classically, and then we can see on the quantum side of things if we can borrow any of these ideas or if any of these ideas extend naturally into the quantum realm. So, as a start, I want to walk you through some of these ideas of what capacity means in classical machine learning. In the beginning, it was thought that we could think about capacity quite simply as the size of our model, meaning that if we make our model, let's say, for example, a deep neural network, if we make this neural network larger and larger, add in more and more parameters in it, then it should be able to capture more intricate relationships. It should be able to express more functions because we are adding more and more parameters into our model, which should be able to capture more intricate relationships in our data. So this was an interesting idea, having capacity be related to the size of our model. But what this led to, or what happened in the field, was really like this seemingly paradoxical behavior that came around with neural networks, where if we had to have capacity on the x-axis now as the size of our model, and we increase our model, we make our model super, super large, what we found was the generalization error does not seem to go up, meaning that no matter how large we make these neural networks, the model just didn't seem to overfit. And yet, we know from Machine Learning 101 that generalization error should start to increase again when we start to create a model that's too high in capacity. So this seemed like a paradox to the community and was actually a common misconception that deep neural networks don't overfit. And let me explain why. The explanation that deep neural networks actually are capable of overfitting came through this very, very nice result in this paper that I listed the abstract of here. And it's called Understanding Deep Learning Requires Rethinking Generalization. So what they showed in this paper was rather interesting. They performed an experiment where they trained a neural network on a data set, on a true data set. So let's say this is the true data set here, pictures of cats and dogs with labels associated to each of the pictures. Then they started to train neural networks, very large neural networks, on data sets where they started to randomize the labels. So now they started to use real data, but started to shuffle up the labels and train those networks. And they were still able to train those networks to zero error, meaning that those networks, those neural networks, were so large that they were capable of even fitting random labels to data. And what they found, very interestingly, was when they trained neural networks, these deep neural networks, on data that contains random labels, the model actually does start to increase in terms of its generalization error. So the generalization error does start to increase again, starts to go up. So the model does in fact overfit when we are training on spurious data, when we are training on relationships that are not true, that are not real. So this meant or suggested that we have been thinking about capacity incorrectly. Initially, I said that we think about capacity, or we started to think about capacity as relating to the size of our model. The bigger our model, the more parameters our model, then the higher the capacity. But the fact that this generalization error performance is related or kind of affected by the data set, like creating these spurious correlations or spurious relationships, affects the generalization error, well, this suggests that we have been thinking about capacity incorrectly, and capacity should somehow incorporate the distribution of data. So a next attempt by the classical community was to look at something called the distribution of margins. And if you remember from support vector machines, the margin is simply, let's draw an example. We have, let's say, some data, and let's say these data comes from different classes, and then we've got some decision boundary. Now, the margin is just simply, the margin of each data point is simply the distance of that data point to the decision boundary, so to the linear classifier in this example. So these are the margins that we can represent as distances to our model, to our classifier. And the distribution of these margins is simply the distribution of these distances of the data points after we have a trained model. So what it was argued was that this idea of this distribution of the margins of our data with a particular model in mind, trained, this should give us perhaps a way to think about capacity that incorporates the distribution of data. And a few very prominent classical machine learning people actually suggested this idea. This came from Vapnik himself, who suggested that since linear classifiers produce these very large margins, well, maybe we can get better generalization performance by understanding generalization using these margins for models. And in fact, margins explained the phenomena of boosting models. So boosting models are models that combine lots and lots of subclassifiers and combine them to come up with a voting rule to predict an answer or solution. So they combine lots and lots of classifiers to produce a more complicated, more robust model. And now it was also a mystery with boosting models that the more we added more and more classifiers, or the larger we made the models, they didn't seem to overfit. And it turns out that these margins, the distribution of margins, explain very nicely this generalization behavior where these models didn't overfit. So one would then think, okay, the distribution of margins could be the answer. The way we think about capacity could be how confident is our classifier, the distance between our classifier and the data points. But unfortunately, margins don't seem to work to capture generalization behavior of neural networks. So there was a very nice paper or result that came out that illustrated this quite nicely. But in short, we can think about how to capture, how capacity measures capture generalization error behavior by looking at this picture again here. And in this picture, remember that when we train our data or our model on data with random labels, we should definitely see this overfitting behavior again. And unfortunately, when we look at the margins of neural networks in this randomization experiment, this relationship does not come through, meaning that the margins, the distribution of margins, does not capture this overfitting behavior that comes with this randomization experiment. And now how do we know that? How can we see that? And this paper really explained this notion of why margins alone are not sufficient to capture generalization behavior quite beautifully. So what you're looking at in this first picture here is the distribution of margins, and this is for two models. A neural network that is trained on a true data set, the CIFAR data set, and a neural network that's trained on a data set with random labels. And so now what you would want to see is a model with large margin has better generalization error performance or generalization performance. But both of these distribution of margins are quite close to zero. So a lot of the margins are very, very small for both of these distributions. So this is not desirable. And this is also, it doesn't really display this behavior that we want to see. right? We don't see this correlation between models trained on true labels versus model trained on random labels. We don't see the overfitting behavior and the real behavior that we should see with true labels. We just see poor margins for both settings. And so what Bartlett and a few other people suggested was that we shouldn't just use margins for capacity, we should actually normalize the margin distribution by some factor that's meaningful. And when they introduced the idea of a normalized margin distribution, then we see exactly the behavior that we want to see with this randomization experiment. So now, if we look at the right-hand side picture, these are normalized margins, and I'll explain what they're normalized by just now. But we are normalizing the margins such that when we look at the trained model, the model trained on random data, we have this undesirable distribution where most of the margins are close to zero. Then, on the other hand, when we have a model that's trained on true data, we have a much more favorable margin. We have a margin that contains much, much larger distances to the decision boundary. And so this normalized idea of margin distributions very nicely captures what we're trying to say with this randomization experiment, where the model trained on random data should be bad, right? It should not, it should reflect this overfitting behavior, and the margin should be bad. Whereas the model trained on true data should have better margins and should have better generalization performance. And so this was quite a cool idea, and it spurred a whole bunch of ideas on how to normalize the margin. So I said that that this paper suggested that the margin alone is not sufficient, and Bartlett in this paper suggested that we should normalize the margin by some constant that depends on the model that we're looking at. And in particular, there were ideas to normalize this based on different norms, and in particular the spectral norm, which is taken with respect to weights of a neural network. But I encourage you to read the papers if you're interested in the technical details. The idea is not, the technical details are not so important in my opinion, but what is important is that we still need to figure out how to normalize these margins in an efficient way. So while the spectral norm was suggested in the Bartlett paper, the spectral norm is respect to every weight matrix at every hidden layer. So in some sense, this normalization still scales with the size of the model, and so might not necessarily be the way to go. And so this spurred really some other suggestions of norm-based capacity measures, and some other ideas on probabilistic settings of how to think about capacity measures. And so I listed some interesting papers over here if you're interested in this idea of capacity in classical machine learning. I highly encourage you to read up about it. But I think what's important to highlight is that in general, finding an appropriate capacity measure, this is still a relevant research question. I think this is still kind of really important to think about in the classical and quantum community, is that we don't properly understand how to assess the true capacity or the true nature of a particular model. And so there's this race trying to find and suggest different types of capacity measures that can do this adequately. And how we assess whether a capacity measure is good or not is really to check if it belongs in these boxes, if it can actually like solve all these little problems. And the first problem is to try and find a capacity measure, for example, that is scale invariant. So if the capacity of the model is scale sensitive, well, this doesn't really make sense, right? So for example, if I have a linear model, say some parameters times our data, and now let's say I just times the parameters by some constant. Now, surely this doesn't change the expressibility of my model, right? And the same goes with like a neural network, let's say. If I were to just times my parameters by some constant, well, the complexity or the capacity of my model should still kind of remain the same. But not all capacity measures are scale invariant. Some of them are sensitive to these shifts in parameters. And so we need to also think about a capacity measure that has this desirable property of being scale invariant. So we don't want it to be scale sensitive. Then is the capacity measure data dependent? Does it actually incorporate data in a meaningful way? So like we saw earlier, if we just think about the size as a capacity measure or the number of parameters, well, this is not enough. We have to somehow include the distribution of data, because that experiment that showed us that neural networks fitted to random data exhibit different generalization properties, well, then data is definitely important in thinking about the capacity of a model. So is a capacity measure data dependent? This definitely is an important thing to tick. Then, for a practical perspective, is the capacity measure that we're looking at even calculable? Can we estimate it in practice? Because this, in reality, is really, really crucial. We don't just want a capacity measure with purely theoretical advantages. We want to be able to use it to assess our models in practice. So being calculable, I think, is also a very important advantage of a proposed capacity measure. And then lastly, does the capacity measure correlate with different generalization error behavior? So as we saw in the experiment, for example, when we train on random labels, we see the generalization error go up again, whereas when we train on true labels, we kind of see it plateauing or being level like that when we train on the true labels. And so we need a capacity measure that can correlate to both of these regimes, where we train on random labels and when we train on true labels. So finding a capacity measure that correlates well with this generalization error is really, really important. Okay, so now how can we think about the capacity of quantum models? Since the capacity question is still kind of open in classical machine learning literature, well, is there anything that we can borrow from there that we can extend to quantum models and help us in understanding how expressive or how many different types of functions can our quantum models express? So there are, of course, a lot of people thinking about this, and these are just some papers that are put up here, but there are many, many more trying to investigate this question of the capacity of quantum models and different types of quantum models and exactly how powerful they are. So I want to make mention of a few interesting ideas and notions, and hopefully they interest you and encourage you to read up more about this and really explore the ideas and the field for yourself. So the first is a paper that I made mention of in a couple talks back. And in this paper, they really try to understand the expressibility of variational circuits. And they looked at a way to measure expressibility was really regarded as, how does my circuit tap into the full Hilbert space that my model has access to or should have access to? And so what that means is, if we take a variational circuit and we start to make it kind of have arbitrary operations in there, how well do we sample from the Hilbert space, from the full Hilbert space? And the more we cover or sample from the full Hilbert space of a particular model, well, then this is deemed as a higher expressibility of a model of a quantum circuit. So in this very trivial example, in this picture, imagine we just had one qubit. And since it's one qubit, we can visualize it in the block sphere. And if we move from a very unexpressive operation like the identity all the way to a arbitrary unitary, we can see that we can start to sample from the block sphere more and more as we increase the expressibility in terms of the unitary, the operation that we apply. As we make this more general, then we can tap into the full Hilbert space. But as you will remember from previous lectures, tapping into the full Hilbert space, creating these ansatz that are just very, very, very expressive is not necessarily always a good thing for machine learning, because with these very highly expressive models, they start to approximate certain circuits with a certain structure or design where the gradients start to vanish. And the gradients of the circuit start to vanish, and the variance around the gradient start to vanish. These are the problems of barren plateaus, which we've heard about before. Now, if we have these barren plateau problems with our model, well, then we can't use nice gradient-based techniques to train them and optimize them. So a high quantum expressivity or a high quantum model expressivity in this regard, as it's defined here, is not necessarily always a good thing. Now, another interesting paper that came out was trying to understand the function expressibility of variational circuits and variational models. So in this paper, what was found, let me say here, in this paper, what was found was this was represented very nicely by this picture over here. And what was noticed, or actually this idea came from originally this data re-uploading paper, where it was found that a model could be made more expressive somehow if we encode our data and repeat our data encoding block often. We encode our data, we apply some variational model, and then we encode our data again and apply a variational model again. And so repeating this or re-uploading our data multiple times somehow affected the expressibility of the quantum circuit. And so in this paper where this picture comes from, the first picture comes from, what they found was that quantum models or quantum circuits designed in this way, where we have encoding followed by a variational block, and then repeated encoding and variational forms, this had a certain structure to it, such that we can actually write down what type of functions this ansatz or this variational circuit can express. It turns out that they can express partial Fourier series in the data, and the coefficients and the frequencies of these Fourier series that the model has access to depend on how many times you encode your data and the structure of the variational form that exists in the model. So this was very interesting because Fourier series are a very rich function class. And in fact, they can be universal function approximators. And so this paper really was a really nice way in showing us exactly how we can write down mathematically what functions we have access to if we design our model in a certain way. And then there was now an attempt to try and understand redundancy in quantum models through something called the effective dimension. And the effective dimension is a measure of capacity. So like we discussed earlier, it's a suggestion for how we can understand the capacity of a model. But the effective dimension's intuition is a little bit different in that the effective dimension really tries to understand how many parameters in your model are truly being useful. So in the world of neural networks, where our models are just have thousands and thousands of parameters in there, how many of those parameters are actually being useful? So we can think of our model, our very, very high overparameterized model, as this very large parameter space. But in fact, only maybe a subset of those parameters are being truly useful. And so the effective dimension tries to understand what is that subset? How large is that subset? And I like this analogy of clouds in the sky. So clouds, we know, are embedded in a three-dimensional space, but their effective dimension, also called their fractal dimension, is 1.37. So the space that they actually occupy in the three-dimensional space is 1.37. And so the effective dimension really tries to do this for a machine learning model. It tries to understand its effective space that it occupies in a much larger space. And so some preliminary experiments showed that quantum circuits, quantum models, seem to just have a much higher effective dimension. So what you're looking at on the y-axis here is the effective dimension, and this is over number of data that we can have. And the effective dimension for a quantum model was just significantly higher in some small-scale experiments. And even as these experiments were scaled up, this relationship existed. And these classical models here are classical neural networks, feed-forward neural networks. So this was seemed promising, right? I mean, if quantum models have these high effective dimensions, then that should mean that our quantum models have more parameters in them that are being useful and being active. But it was also shown that the effective dimension correlates very closely with generalization error. And if you remember from the randomization experiment, this is a good thing, right? We want a capacity measure that shows this correlation to generalization error when we start to randomize the labels. And so what you're looking at here in this picture is the effective dimension here and the generalization error here as we start to randomize the labels more and more and more. So this then suggests that the effective dimension is correlated with generalization error. And so a higher effective dimension for a model doesn't necessarily always mean a good thing, right? Because higher capacity could lead to overfitting, which leads to poor generalization performance. So this leads us to a question of how will quantum machine learning models generalize? Can we make a statement around this? And unfortunately, I don't have the answer, but there are a lot of people thinking about this, a lot of people exploring this idea, and we really need to try and understand this a little bit better, right? Because if we can understand how will quantum machine learning models generalize, we can start to try to think about how to formulate where we can hope for advantages. Where can our quantum models actually perform better? Can we get some benefits in capacity or generalization? Where can we even hope for an advantage in general with quantum machine learning? Is it through some computational advantage? Is it through some statistical advantage? What type of models can we build that offer these advantages? Are they kernel methods? Are they variational circuits? Probably not. Maybe there is an embedding that gives us a kernel that's really useful and classically intractable, classically hard to compute. So, and of course, like there are also problems of data encoding, like the bottleneck of encoding data. How do we get past this? What about scaling of training of variational circuits? How do we combat that? And maybe we can hope for an advantage in some sort of application, but what is this application? So I think in general, we are still kind of, very new to the game here with quantum machine learning. There are so many open questions, so many things for us to think about and wonder and explore and research. And what's great about it is that the field is very fast paced and we don't know so many things. And as a researcher, as someone who's curious in the field, it's a wonderful place to be because you get to think about all these things, you get to investigate them and hopefully answer them. So lastly, I want to just leave you with a short recap of what we've covered in the last couple of lectures. So in the first week, we really went deep into a crash course on quantum computing, where we covered quantum circuits, some basic quantum algorithms. We looked at how noise comes into quantum computation. Then we went into classical machine learning. We looked at how to think about data, data as a mathematical object, how we can pass data to certain models. We dug a little bit deeper into the types of models we get in classical machine learning, then how to optimize them using gradient-based techniques and so on. Then we went into the quantum side of things and looked at a first attempt of building a quantum classifier using a variational circuit, and then how this idea of using variational circuits to optimize for a specific problem was extended to the QAOA algorithm. Then in the second week, we went a little bit deeper into the more advanced stuff on quantum machine learning. We looked at how to think about the right feature spaces when we put data into quantum circuits. How do we do that? How do we build or think about quantum kernels? And then once we had these quantum kernels and this discussion, we then went back to look at quantum models that depend on variational structures and how to train and optimize them. Then we spent a day looking at quantum hardware and how this can affect our machine learning models. And lastly, we ended with some advanced quantum machine learning algorithms that we discussed earlier today. And today we had the discussion of generalization, capacity, and how to think about expressibility or capacity of quantum machine learning models. So with that, I'd like to close this lecture with the fact that you've made it. Congratulations on making it through the course. And I hope that this was beneficial for all of you in understanding how to think about the framework of quantum machine learning and really leaving you with all these open questions of, can we say something about generalization performance? Can we say something about the complexity, the advantages that we can get from computational advantages, statistical advantages, possibilities of how to design models in different ways such that they are useful in a machine learning context? This is very much up to you to go and investigate and find out, and I hope that you are now inspired to get into the field of quantum machine learning. Thank you so much for attending the course and listening to our lectures, and good luck on your quantum machine learning journey.